Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is the basic current divider rule. Our objective today is to apply the current divider rule to simple parallel circuits to quickly and directly solve for unknown current quantities without having to solve for intermediate voltage and total resistance values. The key words are quickly and directly. This should appeal to those of you that have better things to do than perform endless basic Ohm's law calculations to solve for required unknowns. Whatever you choose to do during the spare time is up to you, but the point is you'll have more time to do it if you learn to use the current divider rule correctly. I will admit up front that the current divider rule is a shortcut normally reserved for special case scenarios, and in comparison to the voltage divider rule, is relatively infrequently employed in circuit analysis. This being said, when presented with an occasion in which the current divider rule can be employed, it is as useful as an eye-poking stick when you need to poke someone in the eye. Keeping with the words quickly and directly, we're going to save ourselves some valuable time by referring to the current divider rule henceforth by its initials, CDR. Although this lecture deals exclusively with the CDR application to simple parallel DC circuits, we'll have ample time and occasion to revisit the CDR applied to various branches of series parallel DC circuits, AC circuits, and branches of series parallel AC circuits. Right now, we're zooming in on a very tiny location on a very large map. We'll cross those other bridges and burn them to the ground later. This is a simple parallel DC circuit, and may do us justice to again orient ourselves with previously discussed properties of simple parallel circuits, namely voltage, current, Ohm's law, power properties, and Kirchhoff's current law. For us to incorporate the CDR into our toolbox, all our previous properties and analysis techniques must still hold true, and ideally, this CDR should arrive at the exact same values, albeit in a more efficient and timely manner. Let's see if this is the case. The key properties of this simple parallel DC circuit are as follows. Voltage across elements in a parallel relationship is the same because a parallel connection implies there are only two nodes, across which all two terminal elements are connected. Voltage by its definition is a two-point measurement of potential difference. For this generic parallel circuit, E, our source voltage, equals V1 equals V2. Kirchhoff's current law. The sum of currents entering a node equals the sum of currents leaving a node. What goes in must come out. For this generic series circuit, the Kirchhoff's current law equation is Is, our source current, is equal to I1 plus I2. Knowing the source current and one of the individual currents, we can rearrange the Kirchhoff's current law equation to solve for the other individual current, where Is minus I1 equals I2 and Is minus I2 equals I1. We can use Ohm's law to demonstrate that the current through each element is the voltage across it divided by its resistance. I1 equals V1 divided by R1, I2 equals V2 divided by R2. Given voltage across elements in a parallel circuit is the same, it can be said that the current through each element will be inversely proportional to the resistance. The largest resistor will experience the smallest current draw. The smallest resistor will experience the largest current draw. Let's say R1 is the smallest resistor and R2 is the biggest resistor. If we insert these observations into our Kirchhoff's current law equation, we realize that the source current entering our parallel circuit will be completely distributed through all elements within the parallel circuit, inversely in proportion to the element's resistance value. Underline that term in your notes. You are taking notes, aren't you? Inversely in proportion to the element's resistance value. If R1 is smaller than R2, I1 will be larger than I2. If R2 is larger than R1, I2 will be smaller than I1. Regardless of how current is divvied up between these two parallel paths, I1 plus I2 still equals our source current. Never more, never less. We'll make use of this important observation in a moment. If we wanted to simplify this circuit one step further, we could make use of an imaginary resistor RT, where RT is R1 in parallel with R2. The voltage drop across RT is obviously equal to the applied voltage E, and the current through RT is equal to our source voltage divided by RT. Ohm's law provides additional proof of this. Because voltage across elements in a parallel circuit is the same, It is a like term in our Kirchhoff's current law equation, and we can factor it out, where IS equals E times parentheses 1 divided by R1 plus 1 divided by R2, close parentheses. Using our understanding of the sum of conductance's parallel resistance formula, we can substitute this into the equation, where IS equals E times 1 divided by RT, and in its most simplified form, IS equals source voltage divided by total resistance. Finally, we can use any permutation of the power equations from the perspective of the source or the electrical loads, and make use of the fact that power in always equals power out, where power out is a summation of individual power dissipations. Pn equals P1 plus P2, and we can make use of this fact to check our work. Let's just put some numbers in the circuit and solve it the old-fashioned way, namely slugging it out using repetitive permutations of Ohm's law and hammering it repeatedly until the problem just dies of exhaustion and boredom. This should be absolute child's play to you by now. If it isn't, there is a pressing issue that needs to be resolved immediately. But bear with me, this effort is not wasted because I'm going to use this illustration to make an important point. An unknown voltage source is supplying 42 milliamperes of source current to a parallel combination of a 200 and 600 ohm resistor. I'm asking you to solve for the current through R1 and R2, I1 and I2. By all means, pause the lecture and knock this problem out as a quick warm-up exercise before we learn the current divider rule. I'd hate for you to pull a muscle in the middle of this lecture. The total resistance seen by this source is R1 in parallel with R2. Substituting in the necessary values, we find total resistance to be 150 ohms. The voltage supplied to this parallel combination equals the source current through it times its resistance. Substituting in the necessary values, we find our source voltage to be 6.3 volts. Since this is a parallel circuit, voltage across elements in parallel combination is the same. V1 equals 6.3 volts, V2 equals 6.3 volts. The current through R1 is the voltage across it divided by its resistance. Substituting in the necessary values, we find I1 equals approximately 31.5 milliamperes. We could use Ohm's law to solve for the current through R2. However, we can also make use of Kirchhoff's current law instead. Our Kirchhoff's current law equation for this circuit is IS equals I1 plus I2. Since we were given IS and solve for I1 using Ohm's law, we can substitute these values into our Kirchhoff's current law equation and solve for I2, where I2 is again 10.5 milliamperes. Notice our smallest resistor, R1, had the largest current through it. Our largest resistor, R2, had the smallest current through it. And finally, the summation of all currents equaled the source current. I am reasonably confident we're correct. However, we can use any number of other methods to check our work. The most useful being that power in always equals power out. If you wish to verify the accuracy of our circuit analysis, by all means take the time and do so. This analysis yielded us correct results, and the techniques I employed should not have been surprising or new to you. Before we continue on, notice the numerous steps it took to solve for two unknown current values. Step 1. We needed to solve for total resistance of this parallel combination. Step 2. We needed to solve for source voltage using Ohm's law. Step 3. We used Ohm's law to solve for the current through R1. Step 4. We used either Kirchhoff's current law or Ohm's law to solve for the current through R2. 4 steps for only 2 results. You may be hesitant to consider alternate methods, but trust me, the technique I'm about to introduce to you will yield you 2 results in 2 steps. Our goal is to get the same correct results, only faster. Let's see if this is the case. Here are 2 different permutations of the current divider rule, and they are both wrong. Do not use these formulas. This first formula is the one often presented in textbooks, and it wastes time. The whole purpose of learning the CDR technique is to save time, and this formula defeats that purpose. Do not use this formula. The second formula set is not an all-purpose formula. It's 2 special use formulas that require exact placement of 2 easily confused values. Note the subtle differences between these 2 renditions. Are you going to remember these differences when pressed for time? No, you are not. Do not use this formula set. This is the CDR formula I want you to use. This one will save you time, and it is sufficiently general enough to cover all possible circumstances, including those scenarios not necessarily involving two resistors in parallel, nor even pure parallel circuits, as we'll learn later. Ideally, we'll get the same results, only quicker. Notice the subtle differences in the terminology I've employed and the diagram accompanying the formula. Use this formula, use this diagram with this formula. Any parallel combination of resistors can be described as follows. One resistor is the one you are interested in determining current through. The other resistor is the resistor you are not interested in determining current through. The CDR states that the current through the one I'm interested in is equal to the resistance of the one I'm not interested in divided by the summation of the two resistors times incoming current. Notice I am not using numerical subscripts for the general use formula, nor does this general use formula necessitate solving for total resistance anymore. That's the point. You'll save time, and if you have a modicum of organization skills, you won't get a wrong answer. The mathematically astute among you will realize that the CDR is a proportionate distribution of incoming current, inversely in proportion to the resistor's magnitude. The smallest resistor should draw more current. The larger resistor should draw less. Regardless, all incoming current is divided between these two resistors, no more, no less. A brief comment about the formula before we continue. The numerator, the top of the ratio, is the resistor not of interest. The denominator is the summation of all resistors in that parallel path. Which resistor are you interested in? Which resistor are you not interested in? I don't know. You should know, and you should be organized enough to keep track of which one you're interested in for a particular calculation and which one you are not interested in. Stay organized and use the diagram accompanying the formula. Let's apply the CDR to this same circuit and see if we can solve for the unknown current values quickly and directly. To solve for I1, the current through R1 is our resistor of interest. R2 is our resistor not of interest. I1 therefore equals R2 divided by R1 plus R2 times IN. Substituting in the necessary values, we find I1 to be 31.5 milliamperes. If you're following along with your Texas Instruments TI-89 Titanium Edition Graphing Scientific Calculator or equivalent, by all means, pause the lecture and punch this into your calculator and see if you get the same results. You'll be glad you did. Make the mistakes now, not on a quiz, a lab, or during an exam. Learn from your mistakes and be sufficiently aware enough to never repeat them. The challenge I've observed with students employing the CDR is threefold. Challenge 1. Which resistor are you interested in? Which are you not interested in? Stay organized. I'm not your mama. I'm your electronics instructor, and the only love I know how to give is of the toughest variety. Second, students often struggle entering this formula into their calculator because they neglect to account for the order of operations. Notice R1 plus R2 are both in the denominator. They must be placed within parentheses to make this abundantly clear to the little guy that lives inside your calculator. Without the parentheses, the little guy assumes you mean R2 divided by R1 plus R2 times IN. This will not work. This is not just a wrong answer, it is an absolutely wrong answer. Additionally, some students do the ratio just fine, but then just forget to multiply the ratio by the incoming current. 600 divided by 800, 3/4 or 0.75 is not the answer. 3/4 of 42 milliamperes is. Finally, R1 plus R2 means exactly that, R1 plus R2. It's not the resistance of R1 in parallel with R2. Just add R1 and R2 together. Don't complicate it. That's the point of this version of the CDR. It's easy, it's quick, and does not require supplemental calculation. Since we know incoming current and just solve for I1 using the CDR, we could use Kirchhoff's current law to solve for I2. However, since the CDR is a new toy, I want to play with it till it breaks. Let's use the CDR to solve for I2. This time you're on your own. Pause the lecture and set up the CDR to solve for I2. Once you've got the CDR set up, punch it into your calculator and get a result. Once you've got a result and you're confident it's correct, take a deep breath, steady your nerves, and press play. This time the one I'm interested in is R2. The one I am not interested in is R1. The rest of the formula stays the same. This is the advantage of the quick and dirty general use CDR formula. You don't have to solve for parallel resistance, and you only have to keep track of two resistors, the one you're interested in and the one you're not interested in. Substituting in the necessary values, we find I2 to be 10.5 milliamperes, exactly 1/3 that of I1, because R2's resistance is 3 times as much as R1, and the voltage across them is the same. It makes sense. I1 plus I2 still yields IS. It's just that more of it flowed through the low resistance path of R1 and less of it flowed through the high resistance path of R2. Similar to the analysis I did during the voltage divider rule lecture, look at what we're doing. If you think about it, we're doing the same calculation over and over with only a slight variation every single time. The only thing that ever changes about the CDR formula when solving for current through the resistor we're interested in is which resistor we're interested in. This is another reason why I like shortcuts like the VDR and the CDR. They go well paired with the Texas Instruments TI-89 Titanium Edition Graphing Scientific Calculator or equivalent. These type of calculators typically have a previous results key. Sometimes you can scroll back up to a previous calculation and just wipe out a portion of the calculation you just did and then swap out the numerator. If I walk back up to the calculation I just did for I1, scratch out R2, call the one I'm not interested in R1, and then just press enter, I'd get a result for I2 without even having to enter the equation. Again, what you do with all of this newfound free time is your choice. The point is, you'll have a lot more of it if you start working smarter and not harder and routinely employ shortcuts like the CDR. Notice we quickly and directly solve for two unknown current values with just two calculations without directly having to solve for total resistance or voltage. If we still wanted to solve for voltage, a manipulation of Ohm's law using either of the two elements would yield the same result. With 31.5 milliamperes of current traveling through a 200 ohm resistor, we'd expect V1 to be equal to I1R1. Substituting in the necessary values, we find V1 equals 6.3 volts. With 10.5 milliamperes of current traveling through a 600 ohm resistor, we'd expect V2 to be equal to I2 times R2. Substituting in the necessary values, we find V2 to be 6.3 volts. Again, confirming we can use different methods at different starting points in different sequences to yield the same results. And they all should be correct. Did you enjoy using the CDR? I don't care if you enjoyed it or not. You save time using it. With the time you saved, you can do more of the things you do enjoy. Here's another parallel circuit with the following values. The current input to this parallel combination is 27 milliamperes. Rx is 3.6 kiloohms. Ry is 2.4 kiloohms. Pause the lecture and apply the current divider rule to solve for the current through each element, Ix and Iy. Once you've got this information, solve for the voltage drop across each element, Vx and Vy. The current divider rule states that the current through the one I'm interested in is equal to the resistance of the one I am not interested in divided by the summation of the two resistors times the incoming current. To solve for Ix, the current through Rx, Rx is our element of interest. Ry is our element not of interest. Ry goes into the numerator position. The denominator is the summation of both resistors, the one I'm interested in, Rx, plus the one I am not interested in, Ry. Finally, the incoming current for this parallel combination is our generic current In. The CDR set up to solve for Ix is as follows. Ix equals Ry divided by Rx plus Ry times In. Substituting in the necessary values, we find Ix to be 10.8 milliamperes. Again, we could easily solve for Iy using Kirchhoff's current law, where In minus Ix equals Iy, but since we want some practice using the CDR, let's apply the CDR, where Iy equals Rx divided by Rx plus Ry times In. Substituting in the necessary values, we find Iy to be 16.2 milliamperes. Less current is going through the largest resistor. More current is going through the smallest resistor. The summation of both outgoing currents equals the incoming current. We can be reasonably certain our results are correct. To solve for the voltage drop across each resistor, we can use Ohm's law. Vx equals Ix times Rx. Substituting in the necessary values, we find Vx to be 38.88 volts. Since Rx is in parallel with Ry, it can be said, no calculations needed. That voltage across it is also 38.88 volts. All necessary unknowns have been solved for in 3 quick and direct steps that did not dilly-dally, defer, or delay our immediate satisfaction for results. Get to know the CDR. It will save you time and frustration. Notice at no time did solving for current through or voltage across necessitate solving for resistance of this parallel combination, although you could do this if you wished, using several different methods, notably a restatement of Ohm's law, where RT equals E divided by IS, or your choice of the parallel resistance combination formulas. Either calculation yields 1,440 ohms. This is a great check. Recall, one of the earlier CDR formulas frequently presented in textbooks is Ix equals RT divided by Rx times In, where Ix, the current through our element of interest, is equal to the parallel resistance of this combination divided by Rx, the resistor of interest, times our incoming current. Using this formula, we can also solve for the current through our element of interest. Substituting in the necessary values, we again find Ix to be 10.8 milliamperes. This does yield a correct answer, but necessitated you solve for parallel resistance of this parallel combination prior to using this version of the CDR. You can do this if you want to, but my preferred version of the CDR does not require this step, and it will save you time, not waste it with unnecessary calculations. You'd think it's your choice, but it's really not. I want you to get correct results, and I want you to get them quickly. A brief note about the CDR before we continue. Notice the circuit analysis environment in which it is best employed. If you wanted to spook a herd of buffalo into hurling themselves to death over a steep cliff, there are 2 necessary requirements for a successful hunt, notably a herd of buffalo and a cliff. This is meant to imply that the CDR yields undeniably awesome results, but does require a certain setup in which it is utilized. The CDR is reserved for scenarios in which incoming current is known to be a certain value, and that incoming current divides into parallel paths with known resistances. In theory, current should be as easy to manipulate in circuit analysis calculations as voltage. However, in practice, the deployment of an ammeter to measure current in a real circuit is not nearly as easy as a voltmeter. The primary difficulty stems from the ammeter's requirement that it be placed in series with the element it is to measure current through. This necessitates the circuit be powered off, the circuit broken at its chosen point of insertion, the ammeter must be placed in series with the circuit is intended to measure current through, and then the circuit must be powered back on. This is a serious drag when contrasted to the ease in which voltage measurements can be made. Often a simple check of voltage across these 2 components and then a simple manipulation of Ohm's law to solve for current is far easier than using an ammeter in the CDR. In this case, a voltmeter would read 38.88 volts across the parallel combo of Rx and Ry, and then we use the resistance value of the respective resistor to solve for current through that resistor. If our voltmeter showed that Vx equaled 38.88 volts, the current through it is the voltage across it divided by its resistance. Substituting in the necessary values, we again find Ix to be 10.8 milliamperes. Given these resistors are in parallel, It can also be said that Vy equals 38.88 volts and Iy equals Vy divided by Ry. Substituting in the necessary values yields Iy is 16.2 milliamperes. Given our understanding of Kirchhoff's current law, what goes in must come out. We can then extrapolate backwards that 10.8 plus 16.2, or 27 milliamperes, must have come into this parallel relationship without using the ammeter. Long story short, the CDR is reserved for those situations in which incoming current to a parallel relationship is known, whether you went to the trouble to actually measure it using an ammeter or you calculated it from a previous step. The current will divide between the parallel paths inversely proportional to the resistance of the paths. The path with the largest resistance should have less current, the smaller resistance path more. Regardless, all incoming current will divide between the paths, no more, no less. As alluded to previously, the general use CDR formula is not just limited to applications within perfect parallel circuits, nor those comprising just two parallel resistors. Consider, if you will, application of the general use CDR to this circuit. An ammeter placed as follows in this circuit indicates a current of 30.8 milliamperes is entering a parallel combination of three known resistors. I know there's a lot of other stuff going on in this circuit, but if we restrict our analysis to the elements inside the box, and the box only, we can make use of the general use CDR. Don't worry about what's outside the box. We'll get to that later. The current entering this parallel combination of three resistors should divide between these three resistors inversely proportional to the resistance value. Since RB is the largest resistor at 390 ohms, it should have the smallest current through it. Since RC is the smallest resistor at 130 ohms, it should have the most current flowing through it. Finally, since RA at 260 ohms, being a value between the largest and smallest resistor, it should have a current value between that of IB and IC. The mathematically astute among you will notice the proportionality that exists between these resistance values. RB is 3 times RC. RA is 2 times RC. Should it be a surprise that IC will be 3 times the value of IB and IC 2 times the value of IA? Probably not. Let's see if this is the case. Let's use the general use CDR to solve for IB, the current through the largest resistor. The CDR states that the current through the resistor I'm interested in is equal to the resistance of the one that I'm not interested in divided by the summation of the two resistors times incoming current. Uh-oh, we don't have two resistors. We've got 3 resistors. How can we use the general use CDR formula for this scenario? The answer is cunningly. Recall that we can use any number of simplifications to make our analysis easier. We could perhaps combine RA and RC in parallel into a resistor I'll call R prime, where R prime equals approximately 86.7 ohms. Does this help? Yes, it does. We are now left with a sheer cliff towards which we can drive our herd of buffalo to their end. Which resistor are we interested in when we're trying to solve for IB? The answer is RB. Which one are we not interested in? R prime. The CDR set up to solve for IB is as follows. IB equals R prime divided by RB plus R prime times IN. Substituting in the necessary values, we find IB to be equal to 5.6 milliamperes. Given 30.8 milliamperes is entering this parallel combination of 3 resistors, and 5.6 milliamperes of it travels through RB, where does the rest of it go? Obviously, the remaining current must travel through R prime, which, if we recall, is the parallel combination of RA and RC. What we're doing here is another iteration of Kirchhoff's current law on our simplification, where IN equals IB plus IR prime, and solving for IR prime. Given R prime is the parallel combination of RA and RC, it can be said that IR prime is the undistinguishable lump sum of IA plus IC. We solve for the current through R prime using a restatement of Kirchhoff's current law, but we could have just as easily solved for the current through R prime using another restatement of the current divider rule, where IR prime equals RB divided by RB plus R prime times incoming current, which should again yield 25.2 milliamperes. Kirchhoff's current law is my preferred choice since the algebra is pretty easy, but by all means attempt the CDR, see if you can get the same answer. Again, since R prime is the parallel combination of RA and RC, this lump sum of 25.2 milliamperes being drawn by R prime is really the undistinguishable mass of IA and IC. If you wanted to solve for IA or IC, you can go about this using 3 or 4 different methods. 1. The mathematically astute among you can use the previous observations we made about the proportionate resistance of these resistors, and that RC is 1/3 the value of RB. So RC should carry 3 times the current as RB. Additionally, since RA is twice the value of RC, RA should carry half the current as RC. Very rarely are you given such easily recognizable proportionality between resistors, so I would not necessarily rely upon this step. However, for the mathematically astute among you, that is always an option. Method 2. We can go back to our original parallel configuration of 3 elements and combine RA in parallel with RB into something I'll call R double prime, where R double prime equals approximately 156 ohms. Then we can use the general use current divider rule formula to solve for the current through IC, where IC equals R double prime divided by RC plus R double prime times the incoming current. Substituting in the necessary values, we find IC to be 16.8 milliamperes. Kirchhoff's current law can then be used to solve for IA, where IN equals IA plus IB plus IC. Having been given incoming current and having solved for IB and IC using the current divider rule, we can substitute these into our Kirchhoff's current law equation and solve for IA, where IA is 8.4 milliamperes. There's other variations within method 2 that will yield the same results, but for those with an interest in efficiency, you should be disgusted by the sheer stupidity of this approach. Why backtrack and perform more work? Method 3, move forward and don't look back. Having determined 5.6 milliamperes of our original incoming 30.8 milliamperes went through RB, it can be said, again using either Kirchhoff's current law or the current divider rule, that 25.2 milliamperes entered R prime, which in reality is the parallel combination of 2 elements, RA and RC. Now we can use the general use CDR to solve for one of the currents, then use KCL to solve for the other. Basically, we're zooming in on the details of our previous simplification and applying skills we should be familiar with, notably the CDR. Solving for IA, we find RC divided by RA plus RC times the incoming current. The only trick to this simple method is this: stay organized. Realize the incoming current to this 2 resistor parallel network is not the original 30.8 milliamperes indicated by the ammeter, since 5.6 milliamperes of it already went to RB. The incoming current to this 2 resistor parallel combination is what's left over, the remaining 25.2 milliamperes. Substituting in the correct values, we again find IA to be equal to 8.4 milliamperes. This is far more reliable and more efficient than our earlier methodologies. Finally, consider method 4. Stop being such a hard-headed dunderpate. Why are you going to the trouble of herding more angry buffalo over a dangerous cliff? Go to the bottom of the cliff and start making buffalo burgers. Do not use the CDR more than once. It's annoying and confusing, and you are going to get a wrong answer. Use Ohm's law from here. You solve for current through one of the resistors in a parallel relationship. Solve for voltage across it. VB equals IB times RB. Substituting in the necessary values, we find VB to be 2.184 volts. Since this is a parallel relationship, it can be said, no calculations needed, that both VA and VC are also 2.184 volts. Use Ohm's law to solve for current through the remaining resistors. IA equals VA divided by RA. Substituting in the necessary values, we again find IA equals 8.4 milliamperes. IC equals VC divided by RC. Substituting in the necessary values, we again find IC to be 16.8 milliamperes. We got the same answers and never ran the risk of neither being gored by a horn nor falling off a cliff. Regardless of the method we used, the largest current travels through the smallest resistor. The smallest current travels through the largest resistor, and all incoming current is divided between the parallel paths. IN equals IA plus IB plus IC. Returning to the configuration of our original circuit, everything inside the confines of this box has been solved for. Step outside the box if you dare. My only advice is that you do so thinking of how current travels through this circuit. Are there places where current splits, recombines, or has no choice but to travel a single path? Can shortcuts like the VDR or CDR be applied to other points within this circuit? Will knowledge of current through a particular element give knowledge about the voltage drop across it? Will the knowledge of the summation of voltage drops within this circuit yield knowledge about the necessary voltage rise? This is series parallel circuit analysis, and it is the next step in our evolution of circuit analysis skills. For now, I'll leave the details about these questions unanswered, yet realize you already have all the skills necessary to answer these questions yourself. Trust me, my approach to series parallel analysis is a little different than your $200 textbook or traditional electronics class. Hucksters call series parallel circuit analysis by many names: reduce and return, ladder networks, and assumed value backtrack. You don't need any more skills for series parallel analysis than what you have already, nor do you need to be sold peepstones, snake oil, or magic charms. You have the tools you need. Ohm's law, the power equations, current through elements in series is the same. Voltage across elements in parallel is the same. What goes up must come down. What goes in must come out. Tools like the VDR and the CDR just make circuit analysis faster and more efficient. We'll revisit all these base skills applied to series parallel analysis in the very near future. I'll be pushing you out of the nest very soon. Start thinking about your flight plan. It's your choice to fly or to die. Before we close up shop, let's do one more illustrated example of the current divider rule. This time an example featuring a potentiometer. This circuit features a source of unknown magnitude, supplying a constant 250 milliamperes to a resistor parallel network, one of which is a fixed resistor, RF, at 200 ohms, and the other a 1 kilo ohm potentiometer hooked up in the following fashion: A to B. In this case, the potentiometer represents a variable two-terminal resistor I'll call RL. The potentiometer represents a variable electrical load. For part 1, the potentiometer RAB portion is adjusted to 800 ohms. For part 2, the potentiometer RAB portion is adjusted to 300 ohms. Listen closely to what I'm asking you to do before you rush off and make a mess of this. I'm asking you to use the CDR as one of the steps to solve for the magnitude of the unknown voltage source for both parts 1 and part 2. You are flatly prohibited from calculating the parallel resistance of this combination of two resistors under penalty of extreme death and a hefty fine. Use the CDR. Pause the lecture and take a shot at this. come up with a plan, and execute it violently. Here's how I'm going to tackle the problem. You may have used different methods in a different order, but our answers should agree. For part 1, when RL is 800 ohms, I'm going to use the CDR to solve for IL, the current through the load resistor RL, where IL equals RF divided by RL plus RF times the incoming current. Substituting in the necessary values, we find IL to be 50 milliamperes. Given known current of 50 milliamperes is traveling through the known load resistance of 800 ohms, we can use Ohm's law to solve for the voltage across it. VL equals IL times RL. Substituting in the necessary values, we find VL to be equal to 40 volts. Given RL is in parallel with our fixed resistor, we are aware that the voltage drop across it is also 40 volts. Kirchhoff's voltage law states that this 40 volt drop must be accompanied by an equal and opposite 40 volt rise. The magnitude of our source for part 1 with RL at 800 ohms must therefore be 40 volts. We'll follow a similar methodology to solve for the unknown source magnitude when RL equals 300 ohms in part 2, where IL equals RF divided by RL plus RF times the incoming current. Substituting in the necessary values, we find IL to be 100 milliamperes. Given known current of 100 milliamperes is traveling through the known load resistance of 300 ohms, we can use Ohm's law to solve for the voltage across it. VL equals IL times RL. Substituting in the necessary values, we find VL to be equal to 30 volts. Again, given RL is in parallel with our fixed 200 ohm resistor, we are aware that the voltage drop across it is also 30 volts. Kirchhoff's voltage law states that this 30 volt drop must be accompanied by an equal and opposite 30 volt rise. The magnitude of our source for part 2 with RL at 300 ohms must therefore be 30 volts. Notice it took less voltage to push the same amount of 250 milliamperes of current through the parallel combination in part 2 than it did in part 1. It makes sense. The parallel combination of a 200 ohm and a 300 ohm resistor in part 2 presents less opposition to current than the parallel combination of a 200 and 800 ohm resistor in part 1. What this illustrated example is meant to be is an introductory demonstration of a current source, a basic application of the current divider rule principles. A current source is in effect an adjustable voltage source that maintains current at a constant value regardless of the applied load, at least in a mathematical sense. We'll discuss current sources and source conversion in detail in the very near future. However, realize it's not a particularly hard concept to understand given base skills like the current divider rule and Ohm's law. The adjustable voltage source is continually monitoring the current being supplied and increasing or decreasing its output voltage to maintain current at that constant level, in this case 250 milliamperes. Even if the load resistor was brought extremely low, let's say 3 ohms of total resistance, the current source would still only output a maximum of 250 milliamperes. However, with such a low total resistance, the output voltage doesn't need to be nearly as high as it was previously. In this case, an output voltage of only approximately 738.9 millivolts, or 0.7 volts, would be necessary to push 250 milliamperes through the parallel combination of a 200 ohm resistor and a 3 ohm resistor. This method is utilized by current limited power supplies to keep current below a certain preset maximum and limit the power dissipated by a circuit. Okay, I think we've done enough illustrated examples of the CDR that you should feel comfortable with applying it to these 2 parallel circuits by yourself. I'd like you to pause the lecture and use the CDR to solve for the current through each element in these parallel relationships. Struggle with the problems a little and do not tap out too early. Circuit 1 has a 172 milliamperes entering parallel combination of R1, a 3.9 kilo ohm resistor, and R2, a 2.2 kilo ohm resistor. Circuit 2 has 88 milliamperes entering a parallel combination of 3 resistors, where R1 is 430 ohms, R2 is 690 ohms, and R3 is 1.2 kilo ohms. Fair warning for those still a little bit wobbly on this subject. I am not going to go into details about the solutions, but I will present the calculations I used to arrive at the answers I obtained. You're on your own now. Here's the results I obtained for the first circuit. Pause the lecture and take a good look at how I set up the CDR if you're getting different answers. I1 should be close to 62 milliamperes. I2 should be close to 110 milliamperes. Notice I applied this CDR twice, just so you can get a close look at the setup. However, if I was doing this for time and style points, I would not have done the second iteration of the CDR. I would have jumped straight to KCL to solve for the remaining unknown branch current. Moving on, here's the results I obtained for the second circuit. Pause the lecture and take a real good look at how I set up the CDR if you're getting different answers. I1 should be 44.4 milliamperes. I solved for this by taking R2 and R3 in parallel to be R prime at 438.1 ohms. Then I did my first repetition of the current divider rule. I then used a restatement of Kirchhoff's current law to find the current flowing through our imaginary resistor R prime, in actuality being the parallel combination of R2 and R3. Use this incoming current in my second CDR repetition to solve for I2 at 27.7 milliamperes. Finally, I use Kirchhoff's current law to solve for I3 at 15.9 milliamperes. Notice I applied the CDR twice to solve for this problem, just so you can see it applied internally to a larger circuit. If I was really going for time and style points, I probably would not have done it this way, but rather I would have used the CDR once to solve for I1, then applied Ohm's law from there. As useful as the CDR is for specific scenarios, I'll admit it is not my preferred power move. You'll see when we step into series parallel analysis, I routinely employ the VDR again and again to quickly and directly solve for required voltages and only apply the CDR if backed into a corner. This being said, when backed into a corner, the CDR is a quick way to get out and continue cutting your circuit down to size. In conclusion, this lecture presented the current divider rule and applied it to several simple parallel DC circuits. We found it quickly and directly solved for unknown current quantities without having to solve for intermediate voltage or resistance values. The time you save is valuable. The CDR is quick, it's direct, and it's effective. Remember to review the CDR technique as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.